Hello everyone, welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about the molar fluoride balance algorithm in microreactors. So what is the microreactor? We will discuss algorithm to microreactors. Now first of all we should discuss what is a microreactor. Microreactors are very important and nowadays they are uses. These microreactors are used in various chemical industries. These microreactors are used for the production of explosive products. We can also use it as a chemical sensor. Similarly, when large surface area is required in a small volume, then in that case we are also using the microreactor, because microreactor provide large area in small volume. So the specific surface area which is denoted by small a, which is nothing but the area in the volume of reactors. So the area, specific surface area of in microreactor are very large as compared to conventional reactor like CSTR, PFR, PVR, etc. So the specific surface area can be denoted area divided by volume of reactor, or square meter divided by volume of reactor in cubic meter. It can be square centimeter divided by cubic centimeter of the reactor volume. So the surface area, these microreactor provide large surface area in small volume of reactor. So because they provide large surface area in small volume, therefore we also nowadays use microreactor. Another interesting thing about the microreactor is that the heat transfer and mass transfer resistance in the microreactor are very small. So they provide low resistance to heat transfer, and they also provide low resistance to mass transfer. So heat transfer and mass transfer resistances are very small in these reactors. So we are using microreactor nowadays in various areas, in many areas. For many gaseous reactions we are using the microreactor. So for example, where we can use the microreactor, this is an example. Here we are using the microreactor. The example is a gaseous phase reaction is taking place in a microreactor having width W and height H. So we have a microreactor. The width of microreactor is W. So suppose this is a microreactor. This is the width of the reactor, this one. This is the width of the reactor, or this one is the width of the reactor, which is 0.2 millimeter, and this is the height of the microreactor, this one. This one is the height of microreactor, this one is the height of the microreactor, this is the width of the microreactor, and it is a square-like microreactor. So a square-like microreactor. The component A is entering, reactant is entering, and the product is leaving the microreactor. So the product can be B, suppose it can be B and C, and reactant can be any reactant, and these are the product. And the length of the microreactor is 250 mm. So we have a microreactor. The width of the microreactor is, this is the width of the microreactor, 0.2 millimeter, and the height is also 0.2 millimeter. The length of the microreactor is 250 millimeter. This one is our microreactor. Now what is taking place in the microreactor? A gaseous phase reaction is taking place in this microreactor. Nitrogen oxychloride or nitrosyl chloride is converted in this microreactor into the nitrogen monoxide or nitric oxide and chlorine gas. in the above reactor. So in this reactor, nitrosyl chloride or nitrogen oxychloride, which is denoted by NOCL, nitrogen oxychloride, is converted in this reactor into products. And what are our products? Nitrogen monoxide or nitric oxide, which is in gaseous form, and this one is also gaseous form and also in chlorine gas. So component A is nitrogen oxychloride, component B is nitrogen nitric oxide, and component C is our chlorine. So this is our reaction. The equation for the above reaction is written as 2 mole of nitrogen oxychloride, which is in gaseous form, are converted into 2 mole of nitric oxide and 1 mole of chlorine gas, and all the reactant and product are in gaseous form in this gas-phase reaction. Symbolically, we can written the above equation as 2A give us 2 mole of B and 1 mole of C. 2 mole of A give us 2 mole of B and 1 mole of C. So 2 mole of nitrogen oxychloride give us 2 mole of nitric oxide and 1 mole of chlorine gas in the above microreactor. Symbolically, we can written as 2A give us 2B and 1 mole of C, where A is a limiting reactant. Remember, nitrogen oxychloride here is our limiting reactant. So we can write the above equation like 2A give us 2B plus 1 mole of C. Now divided, this is the stoichiometric coefficient of A, stoichiometric coefficient of B, and 1 is the stoichiometric coefficient of C. So divide this equation by the stoichiometric coefficient of our limiting reactant. So A is our limiting reactant and the stoichiometric coefficient is 2. So divide this equation by 2. Both the reactant and product are divided by 2. So we divided the reactant and product by 2, which is the stoichiometric coefficient of our limiting reactant. So 2 divided by 2, 2 divided by 2, and this is 1, so 1 divided by 2. This 2 cancel with 2, this cancel with 2, and this is 1 divided by 2. So the above equation, this equation can also be written as 1 mole of A give us 1 mole of B and half mole of C. Now, what are given to us? The given data for the above gaseous phase reaction is that the reaction is taking place at 425 degrees centigrade, which is an isothermal reactor. The microreactor is isothermal reactor. This 425 degrees centigrade can be converted into Kelvin when we add 273 Kelvin to 425. We will get 698 Kelvin. So the temperature in the above reactor is the temperature is 698 Kelvin, and the pressure in the above reactor is 1641 kilopascal. So above reactor in the above reactor the pressure is 1641 kilopascal. Now we are entering pure nitrogen oxychloride is entering to the reactor. So pure nitrogen oxychloride here, A is pure. This is pure A. This is 100% pure A, which is entering to this reactor, and it gives us two products, which is nitric oxide and chlorine gas. And the temperature here in this reactor, the temperature is 698 Kelvin and the pressure is 1641 kilopascal. 1641 kilopascal is our pressure in this reactor, and this is the temperature 698 Kelvin. Now we assume the A is pure, which is entering, which is our reactant, and we assume that the microreactor acts as a PFR, plug flow reactor like this one. We assume that our microreactor is like a plug flow reactor. The other value are also given to us, which is Fa0, the molar flow rate of the nitrogen oxychloride at the entering point is 22.4 micromole per second. So FA0 here, FA0, the molar flow rate of nitrogen oxychloride at the entering point. At this point, the molar flow rate of nitrogen oxychloride is given to us, and it is 22.4 micromole per second. 22.4 mole micromole per second. 22.4 micromole per second. It is given to us. The reaction rate constant, which is K, its value is also given to us, which is 0.29 dm cube divided by mole into second at 500. So the reaction rate constant value is given to us at 500 degree, at 500 Kelvin. But the temperature in the reactor is 698 Kelvin. So remember that the K, we will determine the K value at this temperature, not at this temperature. For this, to determine the K value at this temperature, we will use the Arrhenius equation, which is K is equal to K0 E exponential e to the power e divided by R into 1 divided by temperature at this K0, which is T0, which is 500 minus 1 divided by T minus T. So we will use the K value at 698 Kelvin. Now we assume that our reactor is PFR. So this is our PFR reactor. A is converted into B and C. The activation energy is also given to us 24 kilocalorie per mole. Remember that 1 kilocalorie is equal to 1000 calorie per mole, and the 85% of nitrogen oxychloride is converted into product B. So conversion of nitrogen oxychloride is 85% or 0.85. Now what are required? So the required, it is given that you should draw plot and analyze the So requirement, what we are going to determine, plot and analyze molar flow rate as a function of reactor volume down the length of reactor. So the first thing is you should determine that molar flow rate, which is Fj, is a function of reactor volume. So they say that find the relationship between molar flow rate and the reactor volume, which is our flood flow reactor. And the second question is find the volume of reactor at which 85% conversion of A is occurring. So what will be the volume of reactor when the conversion of A in the reactor is 85%? So what will be the volume of reactor at 85% conversion of nitrogen oxychloride? So when 85% nitrogen oxychloride is converted into product B, which is nitric oxide, then at what place of the reactor 85% conversion will occur? So we should determine the volume at 85% conversion of A. This is our second question. This is the second question. Use ODE solver, ordinary differential equation solver, which is Polymer or some other software. But we will use Polymer, which is simple software. So solution, first of all we will use algorithm for microreactor. In the previous lecture we also discussed this algorithm, but in this lecture we will also discuss the algorithm for microreactor. So first step, mole balance on each species. So write mole balance on each species. There are 3 species, A, B and C. These are plug to reactor with VAZU. So take small volume from this PFR, and this is a small volume from the PFR. Molar flow rate of A at volume V, and molar flow rate of A at volume V plus delta V, and delta V is a small volume of the reactor. So FA at V plus delta V, and this FA is at volume V. So we will write mole balance. This mole balance is also given in the first chapter of the element of chemical reaction engineering book, which is written by Fogler. So you can also read the mole balance in the book. We will also discuss the mole balance. So this was our PFR. This is our PFR. Now we are writing mole balance on component A. So we took a small volume of the PFR and we will apply the mole balance. So this was small volume, this is the entering, and this is the outlet of component A. So this is our small volume, this is the molar flow rate of component A at the volume V. So this is V, this is V plus delta V. Yes, please. And this is the V, and this is the delta V volume, small volume. So the molar flow rate of component A at volume V is FA V at molar flow rate of component A at V plus delta V is FA at V plus delta V. Now the general mole balance equation is input minus output plus generation is equal to accumulation. This is the general mole balance equation. So input, this is the input of A, and this is the output. This one is the output, this is the input, this is the output. Input minus output plus generation is equal to accumulation. So that this PFR is at steady state. So this is at steady state. So this term will be 0. Now this is the generation rate. RA is the rate of component A, and this is the small volume of reactor, and the integration over the volume V. Now if rate is constant over the small area, then this term will be come out from the integration, and integral sign will apply to this volume. So this will be nothing but RA into V. So this is the general mole balance, FA entering minus out minus output plus generation, because this was a constant in our reactor, because the volume of reactor was taken in a very small volume, and this is equal to 0. This is now rearrange this equation. Output minus input, rate of component A, in into the change in small and into delta V, change in volume. Now this is the output minus input divided this equation by delta V. So we divide this equation by delta V, which is equal to RA. Now apply the limit. As the volume approaches to 0, then this term will be written as dFA divided by dV is equal to RA. Similarly, this was the mole balance on component A, dFA divided by dV, where V is the volume of reactor. So the mole of component A, which are changes in the volume of reactor, is equal to RA. Now apply the mole balance on component B, because B is also producing in this reactor. So apply a mole balance in same way. So this is the input minus output, and B is generated. So this is output minus input divided by delta V, and let delta V tend to 0, and dFB divided by dV is equal to RB. So this is the mole balance on component B. Similarly, write the mole balance on component C, which is chlorine. So mole balance on component C, chlorine entering, chlorine is producing at this place, entry and outlet, inlet, and when we apply the mole balance, then dFc divided by dV is equal to Rc, the rate of production of component C, which is chlorine. Now, what was our step number 1? Step number 1, mole balance on each component. So we apply mole balance on each component. Mole balance on component A is dFA divided by dV is equal to Ra. Mole balance on component B is dFP divided by dV is equal to Rb. Mole balance on component C is dFc divided by dV is equal to Rc. So this is the mole balance on three components: component A, component B, component C. Now, what is the second step? Come to second. Assume the reaction, this one. Assume that this reaction, which we have already discussed, that this reaction follow elementary rate law. Now, elementary rate law, elementary reaction are those reaction whose stoichiometric coefficient can be written as the order of reaction. So, for example, if this reaction 3A is equal to 4B, if we are written the rate law for this reaction, so it will be written as minus Ra is equal to K Ca to the power 3. This is third order reaction. If this is elementary, if this is not elementary reaction, that this order can be 1, it can be 1.5, it can be 2. So elementary reaction makes our calculation very, very easy. So we assume that the reaction is elementary reaction. So if this is elementary reaction, then in the second step we are going to write the rate law for our reaction. So what will be the rate law for this reaction? What will be the rate law for this reaction? The rate law for this reaction will be written as minus Ra, the rate of consumption of component A in the plug flow reactor is equal to Ka, the rate constant of component A, into the concentration to the power 2. Because this is 2, we have already discussed, so this will come to the power, and the order of reaction is 2. But we can also write the K, we will ignore the A, so it will be written as K into Ca to the power 2, and the rate constant value is given to us 0.29 dm cube divided by mole into second. We have already discussed this. This is given to us. Now, in the third step, in the first step we wrote mole balances. In the second step we wrote the rate law, which was the second order reaction, minus Ra is equal to Kca to the power 2. In the third step, write the relative rates. So relative rate, this was our reaction. In symbolic form, this was our component A, this was our component B, and this was our component C. This was component A. So 2A gives us 2B, 1 mole of component C. So divided by 2, which is the stoichiometric coefficient of our limiting reactant. So divided both sides of this equation by 2. So 1 mole of A gives us 1 mole of B and half mole of C. The relative rate law for this reaction will be minus Ra divided by 1 is equal to Rb divided by 1 is equal to Rc divided by the stoichiometric coefficient of C, which is nothing but 1 divided by 2. So Ra divided by 1, so usually Ra is equal to minus, Ra divided by minus 1 is equal to Rb divided by plus 1 is equal to Rc divided by plus 1 divided by 2. So this minus sign is occurring because A is consuming, the plus sign here is occurring because B is producing, the plus sign here is occurring because C is also producing. And this 1 divided by 2 is the stoichiometric coefficient of C. 1 divided by 2 is the stoichiometric coefficient of C. So we can also write this equation as A gives us B plus half mole of C. So this will come to the denominator here. You can see it. So the relative rate law for the above reaction is this one. So this was our third step. Now we can relate rates of component A, component B, component C with the help of the relative rates. So from this equation we can compare Ra and Rb. So minus Ra is equal to Rb and minus Ra is equal to Rc divided by 1 divided by 2. So Rc is nothing but it is equal to half into minus Ra. So this Rc is nothing but it is Ra, but it is half. This will come to this side and this minus Ra. So here it is Rc is equal to half into minus Ra. So minus Ra. This was our third step. Now come to the fourth step. Come to 4. Concentration is a function of molar flow rate. This is our fourth step. The general relation between concentration and molar flow rate of component J is Cj. Cj is equal to Ct naught into Fj. Molar flow rate of component J, total molar flow rate of components in the reactor, and T naught is the inlet temperature, and T is the temperature at any time, and the P is the pressure at any time, and P naught is the inlet pressure in the reactor, to the reactor inlet pressure. So for component A, this will be Ca is equal to Ct naught Fa Ft into T naught divided by T, P divided by P naught. Similarly, the Ca is equal to Ct naught Fa Ft T naught T P divided by P naught. But here the reactor is isothermal reactor. Isothermal process is occurring in the reactor. This reaction, which was 2A into 2B plus C, or the conversion of nitrogen oxychloride into nitric oxide and chlorine is assumed to be isothermal reaction. So isothermal reaction, the temperature is constant. So the inlet temperature and the outlet temperature is constant and are equal. So this T naught is equal to T. So this term will be equal to 1. And no pressure drop is occurring in this reactor. So pressure drop is also there is no pressure drop. So P will be equal to P naught, and this term will be also equal to 1. So simplify this equation. Ca is equal to Ct naught into Fa molar flow rate of component A and the total molar flow rate of components in the reactor. Now, similarly for component B, concentration is a function of molar flow rate, Ct naught, Fb molar flow rate component B, and Ft. And remember the T divided by T and P divided by P naught is constant, is equal to 1. Here also can be equal to 1. And this Ft is nothing but the molar flow rate of component A plus component B plus component C, which is equal to Ft. Now, for component C, Cc, concentration of component C is equal to Ct naught, the initial concentration of component, total initial concentration, and this is the molar flow rate of component C divided by total molar flow rate of all components, which is this one, which is equal to Fa plus Fb plus Fc. Now what is this Ct naught? This is the concentration, initial concentration, and the initial concentration can be obtained from the ideal gas law, which is Pv is equal to nRT. P is equal to N divided by V into RT, and N divided by V is nothing but molarity or concentration. So CRT is equal to P, RC is equal to P divided by RT. This one, C is equal to P divided by RT. But what will be Ct naught? Ct naught will be equal to P naught, the initial pressure or the entering pressure of the nitrosyl chloride, or the pressure of nitrosyl chloride or nitrogen oxychloride, which is entering to the plug flow reactor. And what is the pressure? It is 1641 kilopascal. R is given to us universal gas constant, whose value is 8.314. T naught is the entering temperature and the initial temperature, which value is also given to us 425 degrees centigrade or 698 Kelvin. So Ct naught is equal to P, putting the value P, this P, value of P is 1641 kilopascal, the value of R is 8.314 kilopascal divided by mole into Vn cube divided by Kelvin, and to the temperature. T naught, which is 698 Kelvin. Kelvin cancel with Kelvin, the kilopascal cancel with kilopascal, and this mole will come to the upper numerator, and this will come to the denominator. So mole per dm cube is the unit, and it is Ct naught value is obtained, which is 0.286 mole per dm cube. So in the third step, in this step we obtain a relation between concentration, and in this fourth step we obtain relation between concentration and molar fluoride of component A, component B, and component C. Similarly, in the fifth step there is no pressure drop, because we already discussed that there is no pressure drop. P is equal to Q naught. There is no pressure drop in the PFR reactor, so this term will be, we will ignore this term. No use of it. So don't use this term in this reactor. Now in step number 6, combine all the above equation. So the combine and solve. So the mole balance equation was dFA divided by dV is equal to RA, dFB divided by dV is equal to RB, dFC divided by dV is equal to RC, but the RA is nothing but the rate of component A, RB is the rate of component B, and RC is the rate of formation of component C in the PFR reactor, which is a microreactor. So we in the second step we show that minus RA is equal to KCA square, because it was elementary reaction. So you can, in place of RA, you can write this relation. So minus RA to this equation. So from this equation, RA will be equal to minus KCA to the power 2, and minus RA is equal to RB, because from relative rate we obtain a relation that minus RA is equal to RB, and RC is equal to half of minus RA from relative rate. So you can come to relative rate. You can come to relative rates like this one. This was our relative rate. This was our relative rate. RC is equal to half minus RA. R minus RA is equal to RB. So you can use the rate in this place. So minus RA is equal to RB, and RC is equal to minus RA divided by 2. So in place of RA, use this equation. In place of RB, you can use minus RA, and minus RA is equal to this one. In place of RC, you can write minus RA divided by 2, and minus RA is this one only divided by 2. So you will get dFC divided by dV. So the dFA is equal to dFA divided by dV is equal to RA, but from the rate law of this elementary reaction, minus RA is equal to KCA, but from the relation between flow rate and concentration, we obtained that CA is equal to Ct naught and to FA divided by FT. Similarly, so the CA square will be equal to Ct naught square FA divided by FT to the power 2. So simply square this term and this term. Minus RA become equal to K rate constant Ct naught square and FA divided by FT whole square. So how can we obtain this? This was obtained in our in this step. We obtained a relation between these relations. From this relation, you can see these relation. This one, this one for CA. Simply this was CD. This was our CC. So this was now. So CA square become this one. So in place of minus RA is equal to, so this is RA minus R, this is RA. So RA we will write, when this minus sign will come to this side, and this will be plus RA minus K into CA square, and CA. square is this one, multiplied by minus k. So minus RA become k Ct naught square Fa divided by the pi Ft square. So multiply both sides by minus. This will become minus k into Ct naught square into Fa divided by Ft whole square. So this minus minus will cancel, and this is plus Ra. This one Ra. So Ra is equal to minus k into Ct naught square Fa divided by Ft whole square. So plug this term in this place, in place of Ra. So dFA is equal to this one. Similarly, for f, dFB divided by dV is equal to Rb, but Rb is equal to minus Ra, and minus Ra is equal to kCa square, and Ca square is nothing but Ct naught square into Fa divided by Ft whole square. So simply multiply by with k, we will get minus Ra. So in place of minus Ra, so in place of Rb we will write minus Ra, and minus Ra is equal to this term. So this term, plug this term in place of Rb, in this place we have plugged it. Similarly for component C, dFc divided by dV is equal to Rc, but Rc is equal to half into minus Ra, and this minus Ra is already determined. So minus Ra is equal to kCa square, and this is kCa square is this one is equal to Ca square. So minus Ra is equal to k into Ct naught square into Fa divided by Ft whole square. So divided it by 2, because this 2 is given. So divided by 2, so it will be equal to this 1 divided by 2 into this k into this one. So dFc divided by dV is we have written dFc divided by dV in term of flow rate. Now open polymath and our other solvers. So now we will find the relation between flow rate and volume of polymath. And the second step was volume. Find volume of reactor at 85% conversion of component A, which was nitrogen oxychloride. So 85% conversion. So this was Fa is equal to Fa naught into 1 minus Xa. Xa is given to us. So Fa naught, the value of Fa naught was given to us 22.6 micromole per second, and this was 1 minus 0.85 become 15% or 0.15. So this was our final Fa, micromole per second 3.39. So in the coming lecture we will use polymath. We will use polymath to find the volume of the reactor and plot graphs of flow rate versus volume of the reactor. Thank you very much for your attention. If you are new to the channel, please like and subscribe.